Hello friends, in first lecture we studied concept of L ordering principle of set of positive integers, which is nothing but every non-empty subset of set of natural number has least element, which is true for set of whole number also. Set of whole number is bounded below by 0. So if I take any non-empty subset of whole number set, it has least element. Any non-empty subset of whole numbers or natural numbers has least element or minimum element. Okay, then we have studied principle of mathematical induction, which is nothing but if P of n is a statement related with natural number n such that P of 1 is true, P of k is true implies P of k plus 1 is true, then given statement is true for every natural number n. And then we have shown that sum of first n natural numbers 1 plus 2 plus 3 dot up to n is nothing but n into n plus 1 by 2. Then sum of the squares of first n natural number, that is 1 square plus 2 square plus dot up to n square, is nothing but n into n plus 1 into 2n plus 1 upon 6. And I have given one exercise that sum of the cubes of first n natural number, that is 1 cube plus 2 cube plus dot up to n cube, is nothing but n into n plus 1 by 2 bracket raised to 2, that is n square into n plus 1 square by 4. Okay, I have given it as exercise. Now we'll take the next example. That is sum of first n odd numbers is n square. First odd number is 1 square. 1 plus 3 is 4. Sum of first two odd numbers 1 plus 3 4, which is nothing but 2 square. 1 plus 3 plus 5, that is 9. And 3 odd numbers, first 3 odd numbers, which is nothing but 3 square, and so on. So here we'll prove it by using principle of mathematical induction. So what is our statement? Pn is nothing but sum of first n odd numbers is n square. We'll take it as one expression number 1. For n equal to 1, left hand side of 1 is 1, right hand side is 1 square, and therefore this implies P1 is true. Okay, step 2, assume Pk is true. P of k is true. That is 1 plus 3 plus 5 plus dot up to, just replace n by k there, 2k minus 1 is equal to k square for k belongs to n. Okay. Now to show P of k plus 1 is 2, that is 1 plus 3 plus 5 plus dot up to 2k minus 1, and next k plus 1th odd number is 2k minus 1 plus 2. By adding 2 in previous odd number, we will get the next odd number. 1 plus 2 gives us 3, 3 plus 2 gives us 5, 2k minus 1 plus 2 gives us 2k plus 1 equal to k plus 1 bracket square. This is our aim. This is our aim. Okay. So LHS 3 is equal to 1 plus 3 plus 5 plus 2k minus 1. I'll take this in one bracket, and this new added term 2k plus 1 in other bracket. By assumption 2, this is nothing but k square plus 2k plus 1 by 2. And then this is precisely k plus 1 bracket square, which is equal to RHS 3. And therefore by principle of mathematical induction, by Principle of mathematical induction. First principle of mathematical induction, Pn is 2 for any n belongs to n. For any n belongs to n. Okay, that is 1 plus 3 plus 5 plus dot dot etc. up to 2n minus 1 equal to n square for any n belongs to n. Next example. Show that 1 cube 1 square plus 3 square 1 square plus 3 square plus 5 square plus dot dot etc. up to 2n minus 1 its square is equal to sum of the squares of first n odd numbers is n into 2n minus 1 n 2n minus 1 2n plus 1 upon 3 for every n belongs to n. Okay. So here Pn statement is nothing but 1 square plus 3 square plus dot dot up to 2n minus 1 bracket square is equal to n minus 1 2n minus 1 2n plus 1 upon 3 n belongs to n. This is my 1 step 1. For n equal to 1, LHS 1 is equal to left hand side of 1 is 1 square is 1, right hand side of 1 is 1 into 2 into 1 minus 1 into 2 into 1 plus 1 upon 3, which is nothing but this is 1 into 2 minus 1 that is 1 into 2 plus 1 that is 3 upon 3 which is 1. This implies P1 is 2. So left hand side is equal to right hand side which is 1. Step 2, we have to prove that we will assume result is true for k and then we will prove that it is true for k plus 1. So assume P of k, that is 1 square plus 3 square plus 5 square plus so on up to 2n minus 1 its square is equal to n into 2n minus 1 into 2n plus 1. Sorry, we are taking k here. K 2k minus 1 2k plus 1 by 3. K belongs to n. This is my 2. Okay. Now to show P of k is true, that is this. To show P of k plus 1 is true, that is 1 square plus 3 square plus 5 square and so on 2k minus 1 is square plus 2k plus 1 bracket square equal to what we have to show k plus 1 into 2k minus 1 will become 2k plus 1, and 2 into k plus 1, that is 2 into k plus 1, 2k plus 2 plus 1, 2k plus 3. Just I am shifting these numbers by 2 to 2 each, because k is getting multiplied by, k is replacing by k plus 1 and multiplying by 2. So we'll get that calculation, right? So left hand side of 3, and then we'll simplify it by using P1 and Pk. So left hand side of 3 equal to 1 square plus 3 square plus 5 square plus dot dot up to 2k minus 1, then 2 into k plus 1, that is 2k plus 2 minus 1, that is 2k plus 1 bracket square. Okay. And we'll take this in one bracket equal. So by hypothesis 2, this is nothing but k, 2k minus 1, 2k plus 1 by 3 plus 2k plus 1 is bracket square. Simplifying it, we'll get k, 2k plus 1, 2k plus 2k minus 1 here, 2k plus 1 plus 3 times 2k plus 1 upon 3. We'll take 2k plus 1 outside, 2k plus 1 into k into 2k minus 1, that is 2k square minus k plus 3 upon 3. Now you have to factorize this. 2k plus 1, if you observe this, 2k plus 1 is here. So we'll check whether this is k plus 1 into 2k plus 3. Sorry, 2k square minus k. 2k plus 1 is taken outside. 3 times 2k plus 1. By taking 2k plus 1 outside plus 3 here, k plus 1 into 2k plus 3 but we are not getting it. What is the problem with this? So 2k plus 1 is there, but other term is not getting adjusting here. So there is some mistake will be in this problem. If I take here 1 square is equal to this. If I take 1 square plus 3 square means n equal to 2. 1 square 1, 9, 10, and then here we'll get 2, 2n minus 1 4 minus 1, that is 3, and 4n, 5 upon 3, that is 10. Okay. Next one. Oh, what happens here? This is my 2k plus 1 bracket square. Okay, so this is 2k plus 1 bracket square. And due to that, there is some mistake here. 3 into 2k plus 1, this term should be there. Due to that small mistake, we are unable to go ahead. Now we'll get it. So 2k plus 1, 2k square minus k plus 6k plus 3 upon 3, which is nothing but 2k plus 1 into 2k square minus plus 5k plus 3 upon 3. Now if you observe here, product of k plus 1 into 2k plus 3, we'll get 2k into k, that is 2k square. This is 3k, this is 2k, 5k, 3. So k plus 1 and 2k plus 3 are factors of that. 2k plus 1 into k plus 1 into 2k plus 3 upon 3, which is the right hand side of 3. And therefore, P of k plus 1 is true. And therefore, by principle of mathematical induction, Pn is true for any n belongs to n. Okay. Again, at the end, you can write what is your Pn statement. Now take next example. Should add 1 into 1 factorial plus 2 into 2 factorial plus 3 into 3 factorial plus dot dot etc. up to n into n factorial is equal to n plus 1 factorial minus 1 for every n belongs to n. Solution. Okay, we'll take this as Pn, my 1. So for n equal to 1, left hand side of 1 is equal to 1 into 1 factorial is equal to 1. Right hand side of 1 is equal to 1 plus 1 factorial minus 1, that is 2 factorial minus 1. 2 factorial is 2 minus 1 is 1. This implies P1 is true. This is our step 1. Now step 2, assume P of k is true. That is 1 into 1 factorial plus 2 into 2 factorial plus dot dot etc. up to k into k factorial is equal to k plus 1 factorial minus 1, k belongs to n. To show P of k plus 1 is true, that is to show 1 into 1 factorial plus 2 factorial and so on, k into k factorial plus k plus 1 into k plus 1 factorial equal to k plus 1 plus 1, that is k plus 2 factorial minus 1. This is nothing but k plus 2 into k plus 1 factorial minus 1. Because we know that n factorial is equal to n into n minus 1 factorial, or n plus 1 factorial is n plus 1 into n factorial. N factorial is product of first n natural numbers. So left hand side 3 is equal to 1 factorial, 2 factorial plus k factorial. We'll take this in one bracket and plus k plus 1 into k plus 1 factorial. Then by hypothesis assumption, that is pk is true, this is nothing but k plus 1 factorial minus 1 plus k plus 1 into k plus 1 factorial. We'll take this k plus 1 factorial outside. We'll get k plus 1 factorial in bracket 1 plus k plus 1. This is from this k plus 1 factorial is taken outside, and this minus 1 as it is. Minus 1 as it is. What is this? This is your k plus 2. K plus 1 factorial into k plus 2 minus 1. K plus 1 factorial into next term k plus 2, that is k plus 2 factorial minus 1. Minus 1. We're getting it here. Okay. Which is nothing but right hand side 3. And therefore p of k plus 1 is true. This implies p of k plus 1 is true. And therefore by principle of mathematical induction, by first principle of mathematical induction, Pn is true. That is 1 into 1 factorial plus 2 into 2 factorial plus dot dot etc. up to n into n factorial is equal to n plus 1 factorial minus 1 for any n belongs to n. Okay. Next example. If r is not equal to 1, then show that a plus ar square plus a into r raised to n equal to a into r raised to n minus 1 a into r raised to n plus 1 minus 1 upon r minus 1. For any n belongs to n. For r not equal to n. Okay. So this is your Pn. So step 1, for n equal to 1, left hand side 1 is equal to a n equal to 1, that is a plus ar. Okay, that is a in bracket 1 plus r. We will get this. Right hand side 1 equal to a into r square minus 1 n equal to 1. So we'll get r square minus 1 upon r minus 1. So a into r minus 1 into r plus 1 upon r minus 1. This r minus 1 get cancelled since r not equal to 1. So this implies LHS 1 equal to right hand side 1 for n equal to 1. And therefore P1 is true. Step 2. Suppose the result is true for, assume Pk is true. Is true for k belongs to n. Fixed k, not for every n. That is 1a plus ar plus ar square plus so on ar raised to k equal to a in bracket r raised to k plus 1 minus 1 upon r minus 1. To show p of k plus 1 is true. That is, this is equivalent to ar square ar plus ar square plus dot dot up to ar raised to k, and next term a into r raised to k plus 1. This must be equal to a into r raised to k plus 1 plus 1, that is k plus 2 minus 1 upon r minus 1. This is 3. This is 2. So we'll take the left hand side of 3. Left hand side of 3 equal to a plus ar plus ar square plus dot dot up to ar raised to k in one bracket and plus a into r raised to k plus 1. By hypothetical step second, it is nothing but a into r raised to k plus 1 minus 1 upon r minus 1 plus a into r raised to k plus 1, which is a into r raised to k plus 1 minus 1 plus a into r raised to k plus 1 into r minus 1 upon r minus 1. We'll take a outside. A outside will get r raised to k plus 1 minus 1 Okay, plus r raised to k plus 1 into r minus 1. We'll get this upon r minus 1 as it is. Then we'll take this r raised to k plus 1, r raised to k plus 1, outside from that two terms, r raised to k plus 1 into 1 minus 1 plus r minus 1, and this minus 1 as it is. This minus 1 as it is. This 1 get cancelled. Then r raised to k plus 1 into this r raised to k plus 2 minus 1 upon r minus 1, which is precisely right hand side of 3. Okay, this implies p of k plus 1 is 2, and therefore by first principle of mathematical induction, Pn is 2 for each n belongs to n. So here we have studied the first principle. There is also revised first principle of mathematical induction with base some n naught. If given statement is true for n equal to n naught, positive integer, and if I have to show that it is true for all n greater or equal n naught, then we'll prove it for n naught. Instead of 1, first we'll prove it is true for n equal to n naught, and then we'll assume result is true for k greater or equal n naught, and we'll prove it for k plus 1, which is parallel to this one. Steps are parallel. Instead of 1, we have to firstly prove for which n greater or equal n naught you have to show. Prove that given statement is true for any integer n greater or equal 7, n greater or equal 10, means my base is 7 or 10 instead of 1. So only instead of P1 you have to first prove that P of n naught is true, then we'll assume Pk is true for k greater or equal n naught, fix k, and we'll prove it for k plus 1, and then by principle of mathematical induction we'll say that it is true for any n greater or equal n naught. Okay, so we'll study examples on this advanced first principle of mathematical induction in next lectures. Thanks for listening lecture carefully. I also request all viewers to subscribe the channel for motivating me, and you can also comment if you need some examples from exercises. You can also comment on it so that I can prepare more lectures from exercises for your understanding better. Thanks a lot. Bye bye.